Welcome to ASMR Chemistry. We're going to be doing some kinetics today. We're going to be analyzing some data and figuring out a rate law for a chemical reaction. All right, but first I need to decide which pen am I going to use. I think I'm going to grab this one. Okay. I have different colors, different pen thicknesses. I think this one's going to serve me well today. All right. So this is a method of determining a rate law known as the method of initial rates. So what's happening here is that there's a particular chemical reaction that's being studied, and then what the experimentalists do is they select concentrations of the different reactants. Okay, they can also do it with a catalyst if that's relevant, but this particular equation here, we're not looking at a catalyst. So these values that you see here, these were chosen on purpose by the people who did the experiment. And then what they did is they measured the initial rate of reaction. This is in molarity per second. Okay, so it's concentration over time of how fast the reaction occurred. And then once they've measured these rates, you can sort through and reason through what was the influence on changing each one of these reactants on the rate. How did it change the rate when you, in this case, tripled the concentration of NO? Or, in this case, you doubled the concentration of H2. And by that, you can then figure out what is the rate law of this reaction. Okay, so that's an overview of the problem itself and the kinds of information you'll be given before you even begin sorting through and solving the problem. Okay. So our first question here is to determine what is the rate law for this reaction. This will always be based on experimental data. You'll have the concentrations and then you'll have the rate. Okay. So let us, I think it's helpful for me anyway, to number each one of these experiments, because that can help me sort through which is which. I'm going to call this experiment 1, this one experiment 2, and this one experiment 3. So we'll give this a header. Okay. So what we want to do is we want to first write out what would be the generic form of the rate law. Okay, so rate laws look like this generically. Rate equals, and then you have a rate constant. And then here you write out what are the reactants. And in this case we have H2. And this will be raised to some power. It could end up being 0, it could end up being 1, it could end up being 2. Those are the three most common that you'll see, but they can take on a variety of numbers, even 1/2, which implies that there's a square root. All sorts of interesting things can happen. Okay, so I'm going to call that, because we don't know what it is, I'm going to call that X. And then we're going to do the same with NO, the other reactant. And put NO here, and that's going to be raised to some value I'll call Y. Okay, so our job is to figure out what is X and what is Y, and then we will know the rate law. Okay, so we want to solve for X and Y. And the way we can do that is by carrying out a pretty neat algebraic trick, and that is if you have an equation, and I know their equal to each other and another equation, you can divide those equations by each other. And this is going to be helpful for us because we're going to have two different rates for two different experiments that were done. We're going to have the same rate constant because this is presumably the same temperature, that's not changing, and it's the same reaction. So the rate constant will be the same. And by virtue of changing what these concentrations are, we will be able to see what is the influence on the rate with x and y and figure out what they are. Okay, so let's see this in action. If you didn't fully follow what I was saying, let's do this idea of taking an equation and dividing it by another equation. In this case, it's going to be the same equation, but just for a different experiment. So let us do this with experiment number 2 and 1. In experiment number 2, we had to triple the amount of NO, where we kept H2 the same. Okay? So what I'm going to do is create a ratio with the larger rate on top numerator. Not everyone uses terms like numerator and denominator all the time, so just as a reminder. Okay. All right. So we're going to do that first. And that means that we want experiment number 2 on top. So that means we have rate 2 will be on top, and that will be divided by rate 1. Making a ratio of these two rate laws. So now we have concentration of H2 for experiment 2, which is 0.10. I made a bracket there. I don't need to. 0.10. Okay, this is in molar. This is the concentration of H2. Okay, this is based on, here's the standard, okay, the rate. This is raised to the x. We still don't know x, so I'll put x there. And then I'm going to put in the concentration of NO for experiment 2. It is 3O. That's raised to the y. Okay. And now I'll divide this by everything that was done for experiment 1. That will match with rate 1. Okay, so we have the form of the rate law. Rate equals K times concentration of H2. For experiment 1, it was 0.10. Oh, I put molar here and I didn't put it there. Let's just keep molar out because they're going to cancel out. It's okay. All right, X. And then what's the concentration of NO here? It's 0.10. Okay, and that's raised to the y. All right, now we can say, all right, let's put in these rate values. Rate for 2, 6.9 times 10 to the minus 3 molar per second, divided by 2.3 times 10 to the minus 3. 3 molar per second. Okay, we're getting somewhere, even if it doesn't seem that way. So look at what has happened. By virtue of the experimentalists purposely choosing one of the concentrations to stay the same, that allows for mathematically, let me get my red pen, mathematically, this actually cancels out. 0.1 raised to the x, 0.1 raised to the x, okay? Look at this, rate constant, it's the same, so cancels out. So this allows us to isolate the influence of changing the concentration of NO on the rate. Okay, so this is 0.30 divided by 0.10. I'm going to show you an algebraic, I don't want to call it a trick, it's just a fact that if you have a number raised to an exponent divided by number raised to the same exponent, you can combine these together into a division here, and the whole thing is raised to that same exponent. Okay. Why don't we calculate what is this ratio, the rates. So we have 6.9 to the minus 3 divided by 2.3 raised to minus 3. It is equal to exactly 3. Okay, if we want to keep sig figs, we could say 3.0, but it is 3. Units cancel out. Okay, what's this? 0.3 divided by 0.1. If we put that in our calculator, we would get 3.0. So 3.0 raised to the y gives 3.0. What does that say about y? When you have a value raised to 1, it gives that same value. Okay, so that means y equals 1. We have solved part of the rate law. Okay, we have figured out what is the exponent that goes with NO. It is 1. Okay, so now our job is to figure out what is x. What is the exponent that goes with H2? So we're going to go through this same process, but now we're going to be comparing. Let's go back to the experiments here. We're going to be comparing experiments 1 and 3. And that is because in experiments 1 and 3, H2 was changed, but NO was not. We want one of them, only one, to be changed at a time, so we can isolate what is the influence of, in this case, doubling concentration of H2 on the rate. All right, so let's see what this is. I always put, again, the larger value on top. Otherwise, I'd get a fraction, and this would be a lot harder to figure out. Okay, so 9.2 times 10 to the minus 3 is bigger than 2.3 times 10 to the minus 3. So I'm going to compare experiment 3 to 1. I'll put rate 3 over rate 1. Okay, so now we're going to do the same thing where we put in these concentrations. All right, this is for H2. And looking at the data for experiment 3, the concentration of H2 is 0.20. 0.20. That's raised to the x. I'm gonna put a little line here to separate these. Okay. And then we can put in concentration of NO. Experiment 3 is 0.10. That's raised to the y, which actually we know what y is, so I could even put in the 1 there if I wanted to. Experiment 1, concentration of H2 was 1.10 raised to the x. And it was unchanged, as it should be, for the NO. Okay, and this is equal to the ratio of the rates that were measured. So we're going to have 9.2 times 10 to the minus 3 divided by experiment 1 gave 2.3 times 10 to the minus 3 molar per second as the rate. So just looking straight from experimental data that was given, 9.2 times 10 minus 3 molar per second. 2.3 times 10 to the minus 3 molar per second. Okay. So let's look again at how we can cancel some things out. And we see that rate constant is the same. It's going to cancel 0.1 raised to the y, 0.1 raised to the y. So once again, we're now seeing what is the influence of, I'll combine this together, 2o and 1o raised to the x gives this ratio. Let's see what this ratio is. Okay. 9.2 raised to the minus 3 divided by 2.3 times 10 to the minus 3. When I said that before, I said 9.2 raised to the minus 3. That is not true. It's 9.2 times 10 to the minus 3. Okay. That equals 4. Nice round numbers. Okay. Units cancel out there. We get 4. All right, so let's take a look at what's going on here. We have 2 divided by 1 raised to the x. So in other words, this is 2 raised to the x gives 4. What do you raise 2, the number 2 to get 4? Yes. If it's squared. Okay, 2 squared equals 4. That means x must equal 2. All right, this is looking good. Now we can go back to the original, again, generic form of the rate law, but now we can write it out given what we know. Okay, so this is how we wrote it out in the beginning. Rate equals k times h2 raised to the x, which we now know is 2, times concentration of NO raised to the 1, where you don't even need to show it. All right, and so we know the rate law. This is fabulous. Okay. Rate equals k h2 raised to 2 NO. All right. There's the rate law. I'm going to put a box around it. Yippee. We got it. But we're not done because let's look at this. It says in this problem, determine the value of the rate constant k. Include the units. Okay, well, we now know the rate law, so we can do this problem. And all we need are some experimental data. And we have 3 different experiments. We can choose any one of these experiments, use the values from them, and we can determine what k is. Okay, so why don't we just go ahead with this experiment number 1, and we're going to put in the values, but I am first going to solve for k. So this was the answer to question A, and now I'm going to put B here, solve for k with rate law, and use numbers from an experiment. Your choice. Which one? Okay, so solving for k, that means we have the rate divided by concentration of H2, that's squared, times NO, And like I said, we're going to use experiment 1 just because there it is. It's 2.3 times 10 to the minus 3 molar per second. We have 0.10 molar squared, and we have 0.10 molar. All right. Let's see what we get in terms of a value, and then we will figure out the units. 2.3 times 10 to the minus 3 divided by 0.1, and then divided by 0.1. That gives us 2.3. Okay. So, okay. 2.3. By the way, some of these, depending on your experience with math, you can do in your head, but I want to show how to go through the entire process. Okay. So, 2.3, what are the units? Okay, so let's sort through this. We have one of these molars. This will just molar, let's cancel out, right? Here we have molar squared, but it is in the denominator. So, we show that with molar minus 2, and then this is per second, seconds minus 1. Okay, there is our rate constant under these conditions. Alrighty, so we have solved this problem. This has been method of initial rates to determine a rate law for a chemical reaction. You're always given the chemical reaction. You are always given the data, and then it's your job to analyze the data and discover the influence of changing the concentration of each one of these species and seeing how it affects the rate. And how it affects the rate is going to be dictated by what are these exponents. Okay, so sometimes you will see that changing the concentration has no effect on the rate. That implies that you would have a 0 exponent. Okay, any number that's raised to the 0 power equals 1. So mathematically it means changing the concentration will have no effect on the rate. All right. So hopefully this is helpful for you, and going through this example of using these ratios of each of these experiments, and then allowing you to isolate what are those exponents on your way to figuring out the rate law. Now sometimes you can do this by inspection, okay? But you also may be asked to show your work. So, but I did want to just show you at the end that you can look at this and say, okay, I see that NO is being held constant, but H2 is being doubled, and I can see here that the rate is being quadrupled. Okay, some people won't see that just by looking, but some people will. It kind of just depends on your experience and how your brain works, honestly. Okay, here's an example where H2 is being kept constant between these two experiments, but NO was tripled. And here you can see by inspection the rate tripled. So that means there is a direct relationship between NO and the rate. NO raised to the 1. Double NO, double the rate. Triple NO, triple the rate. Okay, so that's another method. Not quite as reliable, but it can work. So, alrighty. Well, I hope this was helpful as always, and please do let me know what else I can do for you. Let me know if this video was helpful in any way, and tell me your requests. Always happy to oblige and go through problems for you. I really enjoy doing this, so I appreciate you. Thank you so much, and please like and subscribe. It helps me grow, helps my channel reach more people, and I would just love to teach as many people as possible and help them. So, all right, thanks, and I'll see you in the next video.